All right, we are now done with the really large calculations over molecules and then reactions. Problem 6 and 7 are a little bit more out of the ordinary and a little bit more interesting, maybe. In problem 6, the problem is to just do some heat capacity calculations for the normal modes of benzene. So there's nothing different from what we've been doing already, except for the fact that benzene, of course, has 12 atoms, which means that it has 30 normal modes, which means that even though each mode may not contribute very much, it's possible that all 30 modes together contribute a lot to the overall heat capacity. There's reason to think so because the heat capacity, the measured heat capacity for benzene is quite large, 82.4. If this were a small nonlinear molecule with only translations and rotations, no vibrational contributions, that's the normal kind of rough approximation that you make, the heat capacity would only be about 33, it'd be 4R. That is the heat capacity at constant pressure would be 4R, about 33. That's way smaller, of course, than the actual measured heat capacity, so there's reason to think that the normal modes are contributing. If we want to do this calculation, all we have to do is know the vibrational temperatures for all 30 modes. Since a vibrational temperature is just h nu sub I over k, where nu sub I is the fundamental frequency for a given mode, all we need to know are the fundamental frequencies for all 30 modes, and those were given in the problem, so we can do this calculation. It's just a matter of doing out this 30-term sum, which is a little tedious. That's why I recommend using a program to do it, and that's what I did. All right, now, we can just do the calculation, but it helps to think a little bit about what's going on or what might be going on before we do to see if we can understand the results a little better. If I have a steel bar and it's 1 meter long, then the lowest vibrational frequency for that bar, the lowest bending mode, if you like, the lowest sound wave, really, that can travel in that bar is going to be pretty high frequency. I don't know what it will be, but it'll be high. If I take that same bar, though, and I make it just as thick as it was, just as stiff as it was locally, but I extend it out to 100 meters, so now it's 300 feet long, well, no matter how stiff that steel was, now there's some low-frequency modes, right? This thing will bend and flop and wave and stuff. It's just so long compared to its thickness that now there's going to be some soft modes. And the same thing holds for molecules. If you've got a methane molecule, all the bonds are short, everything's bonded in a tight way. There's just not much room for flopping, and that means, yeah, in that case, there's 4 atoms times 3 minus 6 is still 6 normal modes for that. Sorry, there's 5 minus 3, so that's 9 normal modes for that methane molecule. But the odds are high that there's not going to be any soft ones. They'll all be stiff because the molecule is so compact. On the other hand, if you've got a benzene molecule, which I've drawn roughly to scale here, it's just bigger. There are bigger lever arms. If I grab here and then grab there, I've got a bigger lever arm with which to bend, and that means there's more likely to be some soft modes. So let's look at the results and see what we can understand about all those results. I don't think I'm going to need that page anymore at all, so let me just get rid of it. Here are the results. So this is the output of my program. It was written in C++, but you could get the same output from a whole lot of different approaches, so that doesn't really matter. This column gives the vibrational temperatures. It doesn't give the vibrational frequencies directly, but of course the vibrational temperatures are proportional to the frequencies. So except for a proportionality constant, these are the vibrational frequencies. And you can see that the highest modes are pretty high. They have vibrational temperatures approaching 5,000 degrees Kelvin. But down here at the bottom are the soft modes, and they're pretty low. The vibrational temperatures down here aren't quite at room temperature. In fact, they're still pretty high by our normal day-to-day experience, but they're starting to approach room temperature. And then this column is giving the contribution from each of the normal modes. And you can see that the contributions up here from the stiff modes are pretty negligible until you start getting down here where the vibrational temperatures are starting to be around 1,000, 1,500, and then you start seeing significant contributions to the heat capacity. And finally, when you're down here somewhere in the neighborhood of room temperature, the contributions are getting very significant indeed. If you add them all up, that's what this column is. It's just the running total of all those contributions. The overall contribution is 45, and that is indeed enough. If you add that 45 to the heat capacity for rotations and translations, you get an overall CV value of about 70, and when you add another R to that in order to get the CP value, it's 78, 79, it's almost 80, and that agrees pretty closely with the official value of 82. So there are still some small contributions. Actually, those contributions might just be errors in some of these bond frequencies, some of these mode frequencies. So I'm not sure where the difference is. It could be some small electronic contribution too, or something else in the problem. But anyway, yeah, that's close enough to say that the big difference, the big contribution, the big difference between the rotations and translations and the actual measured value is indeed the vibrations. That's the big contribution. There is one more column here in this table, and that is this column of partition functions, mode partition functions. I put that in there so I could see what the populations were. I could see when the various modes start getting populated, and you can see they really don't get populated until you get down to these last 2 or 3 or 5 modes, and really just the last 2 down there. And even they are barely populated, right? That means that, yeah, the ground state is still the dominant one, but there's a little population in the first excited state, and that's just about it. And the overall population of all modes combined is still less than 2, so we're not getting very much population of the vibrational modes, and yet that's enough to give considerable contribution to the overall CV of the molecule. So it doesn't take a whole lot of population to get a pretty big, especially when there's a lot of modes, to get a pretty big contribution to the heat capacity, and that's the lesson from this calculation. I did another calculation. So this first calculation was at 298 as per the problem, but I did another calculation just for fun at 30,000 Kelvin. So that's 6 times hotter than this, 5 times hotter than the temperature of the sun. I turned the temperature up that high because I wanted to be above the vibrational temperature, even well above the vibrational temperature, even for the hottest modes. And in that case, you can see that now the vibrational contributions from all modes are almost identical. It's 8.3, and it's 8.3 for the stiffest mode and 8.31 for the softest mode. And what that means is that we're now in the high temperature limit for all of the modes. In the high temperature limit, every contribution to the heat capacity is just R. The molar heat capacity is just R, and every contribution to the molar internal energy is just RT. And so in this case, the overall heat capacity would be about 250. Obviously, that's not the case for the actual molecule, but that's the theoretical limit if we were in the high temperature limit for all modes. All right, that's it for problem 6. Why don't we go on to problem 7, actually, since this is a fairly short video so far. All right, so for problem 7, I wasn't actually planning to go to problem 7, so I didn't prepare anything for it, so I hope this goes okay. We'll see. So for problem 7, the problem is to work out some of the statistics and thermodynamics for an Einstein crystal. So for an Einstein crystal, you've got a whole bunch of atoms. It only works for atomic crystals, so metals and things like that. Diamond is the case that you always see in the literature. And the picture is that every single one of these atoms is a little oscillator. It's sitting in the crystal surrounded by the other atoms, and it's oscillating around its equilibrium position. And since it's a three-dimensional crystal, it's oscillating in any one of three different dimensions, and that means there's three different harmonic oscillators associated with every single atom in the crystal. And so every single atom has its own little cue, and if there are n atoms in the crystal, then there will be three modes for every atom, and therefore q to the 3n power will be the partition function for the overall crystal. Normally, for indistinguishable molecules, there would be an n factorial underneath this, but these are distinguishable. All these atoms are distinguishable because they're all stuck in one place. I can tell one atom from the other by its location in space, and therefore it's distinguishable, therefore no n factorial. Every one of the molecular or the atomic partition functions now, or vibrational partition functions, is just 1 over 1 minus e to the minus theta v over t, where theta v is the vibrational temperature, and it's assumed to be the same for every single atom. So if that's the case, the question asks us, first of all, to derive this formula. That was pretty straightforward. Next, it asks us to calculate the mean energy or the internal energy for this particular model. This is a very simple model. It is due to Albert Einstein. And in fact, it more or less revolutionized understanding of heat capacities in his day. Since then, it's been improved upon by Peter Debye and of Debye-Huckel. It's the same Debye as Debye-Huckel. Actually, in physical chemistry, Debye is a bigger name than Einstein. You see Debye all over everything. Anyway, he improved it, and there's now something called the Debye model. It's a good deal more complicated. We won't talk about that this semester. All right. So now we're supposed to calculate the internal energy. We can use this formula, which says that the internal energy is minus the derivative of the log of the full partition function here with respect to beta. The log of the full partition function is just going to be 3n times the log of the one mode partition function, right? This q isn't just from one atom. It's from one direction of one atom. It's one of these guys up here. And so then all we have to do is take the derivative of the small partition function, and that's going to give us a result that's identical to what we have got for other one-mode vibrational partition functions for molecules. And so apart from this 3n in front, which is giving the number of moles in the crystal, and the 3 for 3 modes per atom, it's just a vibrational contribution to the energy. And so that everything should look familiar. Doing exactly the same thing, but for the heat capacity, we know it's just going to be a sum of contributions of one mode contributions to the heat capacity, and that's in fact what you get. And so those are the results for energy and for heat capacity. The next thing to do is actually plug some numbers in, so that's just arithmetic. I guess there's not too much to say except that we then get a heat capacity which is about almost 1 times 3 times n times r. 3 times n times r is the high temperature limit, right? So even though, well, the heat capacity, in this case the vibrational temperature is 290. This is for silver. And so its vibrational temperature is rather low. It's right in line with the with room temperature of 298. So it's actually a little bit below room temperature. And you can see that having the vibrational temperature being close to room temperature, or close to the temperature at which you're interested, puts you almost in the high temperature limit already. So you don't really have to be above the high temperature limit in order to be close to the high temperature limit for vibrational contributions to energy and heat capacity. And I think that's it for number 7. Unless there are questions, people can send me an email And with that, we are done with the practice exam.